everyone, welcome to the lecture number 24 of this NPTEL lecture series on charging infrastructure, and in this lecture we will carry forward our discussion on three-phase AC to DC converter. If we recall what we discussed in the last lecture, so we saw that what's converter look like, three-phase AC to DC converter, which is also called as the front end converter, also called as the active rectifier, we can say. Now in this we are using identical three half bridges, and having through the pole we have connected the inductance L, and then to the source 3 AC source having phase difference of 120 degree, and then we have a capacitor, and this entire converter is feeding to the load RL. And we have seen the operation of this, so we understood that we can control the current which is going into this one by ensuring the voltage across the inductors in a proper manner. That means this side voltage from the source is constant, however from the other side we can apply the variable voltage at a variable phase angle with respect to this source voltage, and that is when we can ensure that there is a current flow either from this source, either from the AC source to the converter side, or from the converter side to the AC source side. So here we can see that whenever there is a power flow which has to be taken place from the AC source to the converter side, we will apply the voltage through the converter at an phase lag of delta, and in that case we ensure that the current is being drawn from the source to the converter and following the unity power factor current. However, when we talk about the backward power flow, that means from the DC side to the AC side, we can ensure the phasor from the converter is actually leading the phasor corresponds to the voltage source by a required angle delta, and by changing the value of this delta we can ensure the current which is going from one AC source to another AC source. We can control the amount of current which is going from one AC source to another AC source. And this particular thing we are talking about, we have only draw this particular phasor for the fundamental frequency component, or you can say for the fundamental frequency. That means our frequency of contention is actually nothing but the line frequency or the frequency of the AC signal. And then we understood the operation. After understanding the operation, we have derived the inductance value which has to be connected in series with all the three sources, and in this we have understood this the value of the inductor should be this much. And here if we see, M is nothing but the modulation index. Now that modulation index is the designer's choice, and they can select the value, and mostly it will be between 0.8 to 0.9. Similarly, the Vs peak is given in the specification, which is nothing but the peak of the AC voltage source, and here we assume that we have the balanced operation where all the three phases are loaded equally. And then here if we see, V naught is again the given in the specification table, because generally in the specification they will mention the output power, output voltage, and the information related to the grid side related to the input voltage, input frequency. Similarly, here is the line frequency also given in the specification. It is a designer's choice. And then the IS peak you can easily predict from the specification table, because we know what is our load power. So we can say this is PL, and it is for the 3 phase, so divided by 3, that is per phase, and we have the V phase RMS, and this will nothing but gives the my current in the RMS value multiplied by root 2. When we do, we will get the IS peak value, and that we can put it over here. This is assuming no loss in the power converter. In other case, you can also take some efficiency term, so we can write, and that efficiency term we can write it in the denominator. We can write some estimated efficiency, let us say some eta, we can take eta of the converter. If we assuming no loss, then we can just take our this relationship to calculate the ISP, and from there we will calculate the L. And once we know the L value, we must ensure that the voltage drop across inductor, obviously in I mean corresponding to fundamental frequency, must be less than 10% of the input peak voltage. That means you can say that omega L times IS peak, that the voltage drop has to be less than 10% of Vs peak. And if you are not getting that, then you again come here and change this value of M modulation index, maybe, or increase the modulation index, and that's when we can able to ensure that the L value changes, and that's when omega L IS peak is less than 10% of Vs peak. This condition has to be ensured. Otherwise, if there is more voltage drop, then the maximum voltage will be dropped across the inductor. So that's why M has to be calculated accordingly. Now after this, let us move ahead and understand how we can size our switches. So we can say sizing of switches. Now you can recall our discussion in the PWM lectures, that means lecture number 22, where we understood that when we have taken the half bridge converter, we understood that the duty ratio for which the switch has to be on is given by 1 by 2 plus Vm by 2 Vc. And here we know that our modulate, this is again modulating signal, and this is our carrier signal. I mean, this we get it from discussions in lecture number 22. So in case of, we can write in case of sine PWM or SPWM, sinusoidal PWM, we can write, so sinusoidal PWM means our Vm is nothing but Vm sin omega t, modulating wave is having the sin omega t variation. So d we can write plus Vm sin omega t divided by 2 Vc, and that will be nothing but, d will be nothing but 1 by 2 plus m by 2 sin omega t, where m is nothing but Vm by Vc. And this is the duty ratio of, if we have taken, I mean if we take just the half bridge, this is here, in this case it is V naught. Now we have the inductor and we have the source, and assume this source with respect to the fictitious, I mean this fixed voltage source I can write using this fictitious O, and this is with respect to fictitious O. If we take fictitious midpoint O, so if we take this one, so if this is A, I am only taking one of the half bridges because we assume that it is a balanced operation of the converter. So all the three phases will also follow the same pattern, obviously with 120-degree phase difference. So now what we see is that this duty ratio of S1 is defined by 1 by 2 plus m by 2 sin omega t, and we will switch the S2 switch for 1 minus, so this is for S1 switch and for S2 switch it is 1 minus D, and that is nothing but 1 by 2 minus m by 2 sin omega t. Now if I have to size these switches, if let us say these switches are made up of MOSFET, if MOSFET is used, if MOSFET with body diode is used, and we ensure that whenever there is a conduction through the body diode, we will turn on, we will form the channel through the MOSFET. So the current will start flowing through the channel. So that is when we have to define the RMS current which is flowing through the MOSFET, and that for that we have to calculate the IRMS. So we can say IRMS of S1 is nothing but, we can write down 1 by T 0 to, going from 0 to T, we can write, so you can see D, and we assume that the current drawn from the source is nothing but Is peak sin omega t, same as that of the Va, which is nothing but Vs peak sin omega t, the A phase source voltage. So we have D times my current, which is Is peak sin omega t square D of t, you can write, and this one, this we can put it 1 by T 0 to T 1 by 2 plus m by 2 sin omega t to Is peak sin omega t square dt. This you can solve to obtain your RMS current flowing through the switches, through the switch S1. Similarly, you can also calculate the IRMS through S2, which is nothing but 1 by T 0 to T. Again T is nothing but 1 by Fs, and we can say that omega t is nothing but 2 pi. Okay, it is going from 0 to T, and for S2 switch the duty ratio is 1 by 2 minus m by 2 sin omega t. So it will be 1 by 2 minus m by 2 sin omega t multiplied by Is peak sin omega t whole square dt. So one can solve these two equations and can calculate your RMS current through the switches if the switch is realized using MOSFET with body diode. Realize S1 and S2 switch. And then in the same way S3 and S4 and S5 and S6 will be there. Now similarly, if let us say if the S1 and S2 switch, if S1 and S2 switch is realized using IGBT with freewheeling diode, using IGBT with freewheeling diode, now if this switch is realized using IGBT with freewheeling diode, then we can draw our one of the half bridges something like this. We have switch S1, and since the freewheeling diode is placed across the IGBT to allow the current in the negative direction, we have placed a diode D1. Similarly, we also have S2 switch and has the freewheeling diode D2. Now this is having plus and minus voltage V0, and that we can just take the fictitious O point and then connect our grid and inductor in this manner. This is nothing but Vs peak sine omega t. Now here we assume that, as you know, we are assuming that our converter is operating with unity power factor. So we have UPF operation, and for now, for easy calculation, let us assume that the current is now being coming out of this half bridge. So we can just define this Is peak sin omega t, as we have the unity power factor operation. So if we look very carefully, when in this half bridge, when the S1 device is on, let us say during the positive half cycle, the current is going from the collector to emitter terminal of the switch S1, which is IGBT. However, during 1 minus dTs period, when the switch S1 is turned off and switch S2 is turned on, because of the direction of current, it will start flowing through the diode D2, and then it will flow back to the source. And let us say, if in case of a negative cycle, when the current direction is in this way. So however, in the negative half direction, when the current direction is this way, the whenever the S2 switch is on, the current will flow through the switch S2, that means between collector to emitter, while when this S2 switch is turns off, then the current will start flowing through the device D1, or you can say through the diode D1. So we can write in positive half cycle, if we assume the current direction in this way, in positive half cycle, when your Vs is greater than 0, we can say that our switch S1 is in conduction for dTs period. Whenever the switch S1 is turned on, the current will start flowing through the switch S1 between collector to emitter, because the current, we assume that current is coming out of this pole of this half bridge. While when the switch S1 is turned off, that means in 1 minus dTs period, when the switch S1 turns off, so because of the direction of the current, since it is coming out of this pole of the half bridge, this diode D2 will turn on, the current will start flowing through the diode D2 automatically. So as a result of which, the diode will be conducting in 1 minus dTs period. And if we see in the negative half cycle, when Vs is less than 0, what we will see is that when the S2 is turned on for during the 1 minus dTs period, the current will, because the current direction will now be going into the half bridge, it will go through the S2 switch, and when the S2 switch turns off, that means during the dTs period, so when the S2 switch turns off, the current, because the current direction is coming into the half bridge, it will start flowing through the diode D1. So we can say that in the negative half cycle, the S2 switch which will be there will be on for 1 minus dTs period, and the D1 diode will be turned on for dTs period, because of the current direction, they are in conduction. And our Ts is nothing but 1 by Fsw, which is switching frequency. So now if we look very carefully, the switch S1, if we see the switch S1, the S1 switch is in conduction for dTs duration, where the D, what we have already know from the previous slide, is nothing but 1 by 2 plus m by 2 sin omega t, and this particular is in conduction for dTs period, during the positive half cycle, only during the positive half cycle. And or you can say the D2 diode is in conduction for 1 minus dts period and duration, and this is again during positive half cycle. And so we can write, so we can easily do 1 minus d, you will get nothing but 1 by 2 minus m by 2 sine omega t. And this, if we take in a general sense, because the switch S1 will only be conducting in the positive half cycle, while in the negative half cycle it will be completely off. So we can write in a simpler manner that I average of switch, particularly we will write for S1, is nothing but 1 by t 0 to t by 2 1 by 2 plus m by 2 sine omega t. And we have during this dt period, during this period the current which is flowing through the switch is nothing but Is peak sine omega t, as we have already assumed it is having the unity power factor operation dt. So when we will solve this thing, what we will get is 1 by t Is peak comes out 0 to t by 2 1 by 2 sine omega t dt plus 0 to t by 2 m by 2 sine square omega t dt. And this, when we solve, what we will get is Is peak by 2 pi 1 plus pi by 4 m. So with this, one can easily calculate what is the average current going through the switch S1. Similarly, we can now define the IRMS switch, for S1, nothing but 1 by t 0 to t by 2 Is peak sine omega t square dt. And that, if we just do and then if you solve this thing, finally you will get peak by 2 root 2 under root 1 plus 8 m by 3 pi. So this is the RMS current which is going through the switch S1. Similarly, you can also calculate the average current for the diode as well. 1 by t 0 to t by 2 is 1 minus d Is peak sin omega t dt, and this, when you solve, you will get 1 by t dt. And this, finally, when you solve this thing, you will get expression 1 minus m pi by 4, which is, this is plus, here it is minus. And then you can calculate IRMS, or you can also calculate the IRMS going through the diode. This is basically for diode D2. D2 is nothing but 1 by t 0 to t by 2 dt, and this, when you put this thing, what we will get is 1 by t 0 to t by 2 minus n by 2 sine omega t. And this finally what you will get is, you will get is peak by 2 root 2 under root 1 minus 8 m by 3 pi. This is IRMS of diode D2. So if we use the IGBT with freewheeling diode, then the switch S1 has to be rated for this RMS value of current, and the diode D2 has to be rated for this value of RMS current. Similarly, the average current of the freewheeling diode D2 should be defined by this expression, and the average current through the IGBT S1 will be of this particular expression. And similarly, if you can also derive for S2 and D1 by putting the appropriate values of limits of integration and duty ratio values, and that is when, by following these particular expressions, one can easily able to predict what will be the RMS and average current ratings of freewheeling diode and the switch, which is an IGBT. And here, this IS peak you can easily calculate from the specification, as we have already told previously, and thus one can easily define the current ratings. And that is when one can actually select the devices accordingly. Similarly, we can also say the voltage stress across the devices, across devices across S1 and S2. If we look very carefully, let us say this is, we are drawing with very V0, and this is a fictitious point O. So it is Vs peak sin omega t, and this is L. And if we see the S1 and S2 switch, so when the S2 is on, the entire voltage V0 is appearing across the S1, and when S2 switch is on, the entire V0 is coming across S1. So we can say that the voltage across this one is nothing but the V0, and we are actually, to provide the safety margin, with the voltage rating of S1 and S2 switch will be nearly, we can take 1.4 times V0, where 40% is nothing but the safety margin. Now this safety margin has been taken because this output voltage will also have some ripple over this. At the same time, when you switch off one of the switches, there the parasitic inductance will come into picture, and that is when you switch off the voltage, the voltage across the switch will look something like this, where this is nothing but the V0, and this is due to parasitic inductance of the loop. This is the voltage across which is S1 and S2. Now this, we know that, let us say if the L parasitic is the parasitic inductance, so this voltage drop is nothing but L parasitic times di by dt. So this will appear across the switch which is actually turning off, and that is why we have to size our switches for that safety margin, and that is why we take generally 40% or 30% of the safety margin. Now if we look our converters, let us look back our converter. If we look our converter, we have actually derived the L value, inductance value, or the RMS current going through the inductance. We have already discussed in the last class. We have understood the voltage and current ratings of the switches. Now the next component is the capacitance. Now let us do the, after knowing our inductance value, switches rating, let us also do the sizing of this capacitance. So first let us do the sizing of capacitance. Now in this sizing of capacitance, let us first try to find, as in the case of single phase AC to DC converter where we did the power balance, and from the power balance we understood that the in single phase AC to DC converter we have second line harmonics component on the voltage ripple of the capacitance. Now let us see what will happen in this particular case when we do the same procedures here. So when we do the same procedure, we can say that the output power we can say that it is nothing but your V naught multiplied by, let us take the power which is coming at that point. So here the voltage, same voltage will be there, but the current is nothing but I converter. And we can also say that our input power, again output power I am talking about here between A point and B point at AB terminals. So input power is nothing but, if we have a 3-phase signal, we can say Vs peak sin omega t, Is peak sin omega t. Again we assume that we have the unity power factor operation, plus again assuming UPF operation. So this is the power at through the A phase. Similarly we can write power at B phase. And power at C phase. This is summing up, and that is nothing but equal to the input power. And now through power balance, if there are no losses in converter, there is or if there is lossless converter, that means whatever power which is coming from here is actually equal to the power at that point. So we can say apply power balance, that means input power is equals to output power. Obviously this we are saying instantaneously as well as the average power, and that's when we can say that V naught times I converter is nothing but equal to Vs peak sin omega t, Is peak sin omega t plus Vs peak sin omega t minus 120 plus Is peak sin omega t minus 120 plus Vs peak sin omega t minus 240 to Is peak sin omega t minus 240. Now this when we do, we can take out Vs peak, Is peak is nothing but sin square omega t plus sin square omega t minus 120 plus sin square omega t minus 240. This when we write Vs peak, Is peak 1 minus cos 2 omega t by 2 plus 1 minus cos 2 omega t minus 240, because 2 times of that, plus 1 minus cos 2 omega t minus 480 divided by 2, and this will comes down to Vs peak, Is peak into 3 by 2 minus cos 2 omega t plus cos 2 omega t minus 240 plus, now 480 we can write 360 plus 120, so we can say nothing but cos 2 omega t minus 120, and this term, this entire term is nothing but equal to 0 at any given instance of time. So we can say that V naught I converter is nothing but, if we see that, 3 by 2 Vs peak Is peak, and that is nothing but my I converter is nothing but 3 by 2 by V naught Vs peak Is peak. Now if we see, there is absence of, that indicates there is absence of, there is no second line frequency component. So there is absence of second line frequency component. So if we look very carefully in this converter, this particular current has only the DC component, and there is no second line harmonic component, there is no third, there is fourth, there is no lower order harmonic component in this I converter current, and only the high frequency currents will be there in this I converter current. Because in this particular derivation we have only take line frequency component of the current, and we know that during the operation along with this line fundamental frequency component we are also having the high frequency component, voltage component are also there. So that is when you will have high frequency current as well. So we can say that here there is absence of second line harmonic component, only DC component exists, only DC component exists, there is no second line frequency component. In case of single phase converter we have the second line frequency component, and that is the reason why we could not take 3 single phase converter. Instead of taking 3 single phase converter, we have taken the 3 half bridge based converters, and we are making them operate in a balanced 3 phase manner. So that is the reason why this will result in small capacitor size for 3 phase AC to DC converter, which was not the case when we will use 3 independent single phase AC to DC converter, as all the 3 single phase converters will have the second line harmonic voltage ripple at the output capacitor, thus require 3 large capacitors to keep the output voltage ripple within the limits. So that is the reason why the 3 independent single phase converter is not preferred. Instead of that, single 3 phase converter with 3 half bridges operated with 120 degree phase difference is being used. And when we do that, we ensure that there is no presence of second line frequency component in the I converter current, and that is when there is no second line harmonic component in the capacitor voltage. Now what would be the next frequency component which will be present in the I converter, because that frequency component will be flowing through the capacitor and the DC will be going through the output load. So let us try to see what would be the component of current which will be present in this I converter current. So we know that for the fundamental frequency we have drawn the equivalent circuit, single phase equivalent circuit to be like this, where here we have Vs of t, L, and we have V converter with respect to time t, and we have current Is of t going. Now we know that our V converter has fundamental from the lecture 22. Our average variation of pole voltage is nothing but has the fundamental component, frequency component, and along with this harmonic frequency component at side bands of MF. which is nothing but MF is nothing but my FC by FM, or you can say that fundamental frequency. And here our fundamental frequency is our line frequency. So in this case what we see is that the V converter T has fundamental component, and along with that we have harmonics component. So when we draw the, this is when for the fundamental frequency, this is the single phase equivalent circuit. So here we have seen that because of fundamental frequency component, there is no introduction of harmonics in the I converter, and thus there is no ripple on the output capacitor voltage. It is just the DC quantity. So let us see what will happen when we draw the circuit for harmonic frequency component. So for a harmonic frequency component, the single phase equivalent circuit will look like circuit will be, if we see, since the source has pure AC source, so there is no harmonic frequency component, so that is why the source will be short circuited, while we have this L, and along with that we have our component which is nothing but V converter N, where N, or V converter of N, where N is the harmonic component, and that harmonic component will be at the side bands of MF, which is side bands of carrier frequency, you can say. So what we have is, we have the circuit like this. Now because of this circuit, there will be current through this circuit, IS of that particular frequency component. So we can say that IS of N is nothing but V converter of N, let us say if it is with respect to T, so we can say with respect to T, divided by, here now this impedance L which is there will not now be N times omega what we have, which is N omega L, where omega is nothing but 2 pi FM, or here our FM is nothing but our line frequency, so we can say omega is nothing but 2 pi Fs. So what we see is that because of the fundamental component, we have the component of current which is having the fundamental component. So the current will have the fundamental component, which is nothing but, we assume to be having a unity power factor current. So it is sin Is peak sin omega t, which is which we obtain over here, and because of the harmonic frequency component in current, so because of that what we have is, we have harmonics along with this pure sinusoidal current, we also have the harmonics current, and that harmonic current will actually introduce harmonic component of current in the I converter, and that will be harmonic current has to be filtered out by capacitor C, while the DC current will be going through the load RL. So what we understood, in the case of fundamental frequency component, for the fundamental frequency component, the equivalent single phase equivalent circuit will be having, we have the VST and we have the omega L impedance, and then we have the V converted T. I mean here again it is J omega L, and here we can also say it is J n omega L, and here again we can say it is J n omega L, and that corresponds to the current which is nothing but Is peak sin omega t, because we are assuming that we have the unity power factor operation. So that current is the fundamental component of current. However, along with this fundamental component, we also have the harmonic current, and that harmonic current is happen because the output of the half bridge, which is the average pole voltage variation, has the fundamental component, and along with that it has the harmonic component which is at the side bands of MF, or side bands of you can say the carrier frequency, which we have studied in lecture number 22, and that is when we can see that this harmonic component of current will result in the presence of harmonic component in I converter, which corresponds to the AC component of current which is flowing through the capacitor, and that we will derive in the next class to understand the RMS current rating of the capacitor bank, and then we will see how we can calculate the value of capacitance afterwards. So thank you very much for listening to this lecture, and we will continue our discussion on how to size our capacitor bank, because the capacitor bank is very important, because in here in case of single phase what we have understood, we understood is the dominant component of current which is going through the capacitance is the second line harmonic component, and that is when we design the capacitance corresponding to that second line frequency component. But here in this case, in case of three phase converter, that there is no second line harmonic component of current in the I converter current, and that is when there is no second line harmonic component of voltage onto the voltage ripple onto the capacitor. It will only have high frequency component of current. I mean, the I converter only has the high frequency component of current, and that value of current will be flowing through the capacitor, which will correspond to the ripple in the capacitor. However, that harmonic component of current are having the lesser amplitude, and that we will see in the next class how that current will look like, and then from there we will stabilize our understanding on sizing of the capacitor bank. Thank you very much for patiently listening to this lecture.